5.3 metal and non-metal oxides. Let's start with basic word oxides itself. So oxides are actually binary compounds of oxygen. When I say the word binary compounds, binary means two compounds that are made up of two elements. So of course, as the name oxide is there, so that means that one of those elements forming the compound would be oxygen. The second element can be anything. If that second element is metal, we call them metal oxides, simple naming. And if that second element is not non-metal, we call them non-metal oxides. Now, I'm going to directly jump to the next page, and page number 126 has a diagram at the bottom of the page which clarifies it further. Now take a look. We have non-metal oxides and we have metal oxides. Both of them are further bifurcated into two subcategories. If I talk about non-metal oxides, they are converted into acidic oxides and neutral oxides. If I talk about metal oxides, they're converted into amphoteric oxides and basic oxides. I'm going to rearrange them a little bit differently so that you'd understand what they are. So acid oxides are explained as oxides that are made up of non-metal and they act like acids whenever they are dissolved in water or reacted with a base. Okay, and basic oxides are the oxides which are made up of metals and they act like bases or alkalis when dissolved in water or reacted with acids. Then we have neutral oxides. Neutral oxides act like none of these. They're neither acidic nor a basic. So they usually don't even dissolve in water. At least some of them don't. Lastly, amphoteric oxide. And amphoteric oxide is actually a combination of both. They act like acidic oxides as well as basic oxides because they're going to act like acids whenever reacting with alkalis. They're going to act like bases whenever reacting with acids. So, as the name suggests, acidic oxides act like acids, basic oxides act like bases, amphoteric oxides act like both, and neutral oxides do not act like any of these. Okay, that's how easy it is. But this topic is not just about oxides. This topic has much more to offer. Now, this topic has a big table on this page number 126 top, table 5.5, and they literally start off from the element that we are naming for the oxides and how it reacts with oxygen. What is the product, the name, the formula, or the look of the product, whether it is white or colorless or colored, or is it a gas or solid or liquid, whatever that is, and what's the effect of adding water to it and testing it with litmus paper. So they have divided this huge table into two parts, non-metals and metals. So this table seems easy, but let me tell you, yeah, this is easy. I'm not saying it's difficult, but this the table only consists the information in the form of words. Now, if you take a look at past 10 years past papers, you'll find that this table isn't always comes in the form of words as a part of the paper. Actually, many of the questions pick out some equations out of it. So what we need to do is to convert the words into equations. And that's where this table becomes interesting. And that's where we need to add the information. Okay. So I'll keep on writing information. I'll keep on explaining at the same time. And I'll keep on adding more stuff to this table. Make sure you follow. Make sure you keep on writing. Okay. Let's get started. Let's start with sulfur. Sulfur burns with a bright blue flame. Now, in order to understand what that means, the diagram is present in the previous page 125. You can see sulfur and you can even literally see that blue flame. Now, this is sulfur being burnt in a jar or gas jar of oxygen. Sulfur is burnt in pure oxygen. You can see the blue color. If you're burning it in air, yeah, blue color is visible, but a little bit distorted. So that's easy. Let's move on to the table, back to the table. Let's keep on writing. So the equation must be simple and easy. S plus O2 giving us SO2. That's what we have made over here. A colorless gas named sulfur dioxide, the formula SO2. Now, when we dissolve it in water, it turns litmus paper red. So SO2 actually can be dissolved into water and it forms H2SO3, which is known as sulfurous acid. Sulfurous acid. And since it's an acid, it can easily turn the litmus paper from blue to red. That makes much more sense now. Okay. Phosphorus. Phosphorus burns with a yellow flame. If we talk about phosphorus, it exists in the form of P4. It can easily react with 5 molecules of oxygen, forming P4O10, which is a white solid, or which is also abbreviated as P2O5. In fact, let's not write P4O10. Let's go with this differently. So that's 5O2, and that gives us 2P2O5. Okay. So when we dissolve this P2O5 into water, it forms H3PO3. Okay, let's see if we can balance this equation out. Actually, this is going to be H3PO4, so I am going to rearrange it a little bit. H3PO4. And remember, H3PO4 is phosphoric acid. Since it's an acid, it can turn the litmus paper from blue to red. So P2O5 reacts with 3 water molecules, gives us 2 molecules of H3PO4 phosphoric acid, which we studied at the start of this chapter, and that's how it's capable of turning litmus paper from blue to red. All right.
Yes, sir.
Next up is carbon. Carbon glows red. We've seen uh, coal pieces glowing red whenever they catch fire. But this forms a colorless gas, carbon dioxide. The equation is pretty simple. C plus O2 gives us CO2. This dissolves slightly and slowly turns a litmus paper from blue to red. Why? Because carbon dioxide can react with water to form a weak acid by the name of carbonic acid. H2CO3 is the formula for carbonic acid. All right. Okay, when we
Yes,
talk
sir.
about nonmetals, I say that there is something missing from this table. So it does not exactly give us colors when it reacts, but the reaction is possible. So I'm going to add one more element to it. Instead of writing it at the bottom, I'm going to write it at top. That is nitrogen. Since nitrogen is a colorless gas, this reaction does not specifically show us any color. So it forms a colorless gas. Actually, let's not go with colorless gas since it would be difficult for you then. So brown gas, that is nitrogen dioxide. The formula for which is NO2. The equation is going to be NO2 plus O2 giving us 2NO, which upon further oxidation or reaction with oxygen forms 2NO2. Now this NO2 reacts with further oxygen and water to form, this is 2H2O, 4HNO3, and we know this is nitric acid. And of course, it's going to dissolve and turns litmus paper from blue to red. This completes the non-metals part for us. Make sure you note everything down, and when you're done, let me know.
Yes, sir. I'm downloading.
Alright, so I am going to clear all of this up, and we're going to start with metals. Okay, moving on with
Okay,
metals.
sir.
The first one is sodium. It burns with a persistent yellow flame. Sodium reacts with oxygen in such a way that 4Na plus O2 gives us 2Na2O. That's the equation. It's a white solid. We call it sodium oxide, the formula for which is Na2O. Now, Na2O can easily dissolve in water. That happens really quickly, and it forms the famous alkali sodium hydroxide. Sodium hydroxide is famous and is a strong alkali. It can definitely and easily turn the litmus paper from red to blue. Next comes magnesium. Magnesium burns with a bright white flashy flame. This flame is similar to the flashlights that we observe commonly in our own flashlights, the flashlights that are equipped in the cell phones or different other electronic equipment. Now, this reaction is also pretty simple. So, magnesium 2Mg plus O2 gives us 2MgO. Magnesium oxide also dissolves slightly, and it turns litmus paper from red to blue because it can also form the hydroxide for magnesium, the same type, that's magnesium hydroxide. I'm not going to write the name since I don't have enough space. So that's magnesium hydroxide, pretty much similar to how we have written sodium hydroxide. Make sure you write it. Next up is calcium. Calcium burns with a red flame. It has somewhat a brick red color of the flame. Now these flame colors are important, and you are going to see the questions about these flame colors in all three papers: paper 2 MCQ paper, paper 4 the theory paper, and paper 6 the ATP paper. Out of these three papers, you're going to find questions mostly paper 2 and paper 6. Flame colors are commonly a 1 mark question, and they literally just need to know the color. If you tell the color correctly, you get the mark. Now this forms a white solid, calcium oxide, CaO. The equation is pretty similar to what we wrote for magnesium. 2 calcium plus oxygen gives us 2
Okay.
calcium oxide, right? Jipita?
Won't we balance the equation for magnesium when it reacts with water?
Magnesium oxide in water, beta?
G, won't we balance it?
It's already balanced. MgO plus H2O gives us MgOH twice. Are you talking about the magnesium oxide equation? Because that one is already balanced.
Oh, okay.
Are you talking
Okay,
about this
sir.
one or some other equation? Because I didn't get it.
Yes, I was talking about this one.
Okay, beta, this one is already balanced. You won't need to balance it any further. Okay,
Okay,
and
sir.
calcium equation is no different. If I just replace the symbols of magnesium with calcium, you'll find the equation pretty much similar. So CaO plus H2O is going to give us CaOH twice. And just like we named it for magnesium as magnesium hydroxide, or for sodium as sodium hydroxide, this one is calcium hydroxide. Again, these are all alkalis. They can all dissolve, whether slightly or completely, they do dissolve, and they can easily turn litmus paper from red to blue. So the same pieces of information come over here. Now, sodium, magnesium, and calcium are all simple normal elements. None of these are transition elements. But the next two examples are of transition elements, iron and copper. And from here on onwards, you'd notice the normal elements and the way they react, or the effect of adding water, or the effect of testing it with a litmus paper is different for normal elements in comparison to transition elements. Let's discuss about the transition elements. Let's start with iron first. Now, iron burns with yellow sparks. It forms a blue-black solid, that is iron oxide. Now, wait a second. Blue-black solid? Okay, yeah, fine. Iron oxide FeO, so the reaction is pretty simple. 2Fe plus O2 gives us 2FeO, right? FeO is insoluble in water. Since it does not dissolve in water, you can't form a solution, you can't test it with a litmus paper, and that's why this whole area is missing as a part of information. Okay? The last one on the list is also a transition element, copper. Copper does not burn, it simply turns black. Let me tell you, not to forget, copper is different from most metals. When most metals have a silver gray appearance, this is the only metal which has a red brown appearance. So the color of copper is red brown. When this red brown color changes to black, it's pretty visible. So this black solid is copper oxide, and the reaction is literally the same as iron. 2Cu plus O2 gives us 2CuO, copper 2 oxide, and likely, as in comparison, the transition elements compound like iron 2 oxide, copper 2 oxide is also insoluble. Hence, we can't form a solution and we cannot test it with a litmus paper. Now, this finishes the whole table. This table gives us the idea of talking about acidic oxides or basic oxides. But this does not just end over here. The reactions for oxides with acidic oxides, either with alkalis or basic oxides with acids, are similar to neutralization reactions in terms of product. We usually form salt and we usually form water along with it. If you're done writing these, we can move to the bottom of this page and I can write further equations for your understanding.
Yes, sir, I'm done writing.
All right, so I'm going to clear it up. Let's move. So the important pink portion, characteristics of oxides. Non-metals generally form acidic oxides. They dissolve in water and they form acidic solutions. Metals, on the other hand, generally form oxides that are solids. They dissolve in water. These oxides give alkaline solutions. Metal oxides neutralize acids and hence are known as basic oxides. So, if they can neutralize acids, let's take some examples right out of the names or compounds given over here. Let's start with acidic oxides. So, we're calling them acidic oxides. Why? Because they act like acids. Let's talk about carbon dioxide. Carbon dioxide is an acidic oxide, the first example over here. Now, this can react with NaOH, and this can form salt along with water. Now, this is pretty much similar to an neutralization reaction. Acid plus alkali gives us salt plus water. In this case, it's not acid plus alkali, it's acidic oxide plus alkali giving us salt plus water. If I don't take this example, if I talk about a different one, let's say we talk about SO3, I'm picking up a random one from here. It reacts with, let's say, KOH, another, a different alkali, right? So what happens, it's going to form K2SO4 plus, it's going to give us water. So again, an acidic oxide plus an alkali giving us salt and water. I hope that makes sense, right?
Yes, sir.
When you're done writing, let me know so that we can move on to basic oxides. Are you done writing?
No, sir, I'm writing the last one.
All right.
Yes, sir, done.
Okay, so I'm gonna erase this whole thing up and let's talk about basic oxides now. So I am going to quote similar examples with basic oxides. It's just that since they're basic oxides, let's consider the first example, CaO. We are going to react it with an acid. Let's consider the example of HCl. Now, this reacts, forms a salt, calcium chloride, CaCl2, plus it forms water, H2O. This is pretty easy. Let's consider another example, Na2O, sodium oxide. Let's consider a different acid this time, maybe nitric acid, right? So it forms the salt, sodium nitrate, NaNO3, along with it forms water. So this time it's a basic oxide and an acid reacting to form a salt in water in both the reactions. So that's why we are able to call it a basic oxide. We've already discussed that when we try to dissolve in water, most of them do dissolve in water and they produce good alkalis. Since it is also capable of neutralizing an acid in the similar way a neutralization reaction goes, which is acid and alkali producing salt and water, this reaction also produces salt and water. So the basic oxide is actually proving itself acting like a base.
Okay,
Let me
sir.
know when you're done writing.
I'm done, sir.
Okay, next up are amphoteric oxides. As I've already explained, amphoteric oxides act like both. This is also given over here in the key definition. Amphoteric oxide or a hydroxide, since both are possible, they react with both an acid and an alkali, and can give salt and water. So they react like an alkali with an acid, or they react with an alkali like an acid to give salt and water. So they give salt and water in both the cases. Now, the example of forming a hydroxide, such as zinc hydroxide, is over here. But exactly to talk about how they are going to react with an alkali, reactions are given over here. With acids, the reactions are not given over here. All right. So this is something missing over here. They do quote the names of zinc hydroxide and aluminum hydroxide as amphoteric oxides. They do quote their reactions in word form, but these reactions are missing the other parts and they are not in symbolical form. So this comes as a disadvantage. What we are going to do is that we're going to quote these reactions here for amphoteric oxides in symbolical form, chemical equations, proper equations. Okay, for amphoteric oxides, the list can be given like this. Since we are talking about both oxides and hydroxides, so I am going to write all possible examples that can be a part of IGCSE or have been a part of IGCSE. So these are six compounds which have been a part of IGCSE before. Now, beryllium is something that you're going to see as an example and a really, really old example way back, like 10 years or 11 years back, just once. However, zinc and aluminum examples are the most common ones and have been discussed in past papers way too many times. Now, since it's an amphoteric oxide, just writing an equation to prove it an acid won't be good enough. We need one equation to prove it as an acid, one equation to prove it as a base. So we need two different equations. Let's pick one of these. I'm going to pick zinc oxide and I'm going to react the same compound with an acid and, of course, with an alkali. Now, when it reacts with an acid, it forms a salt, zinc chloride, and it forms water. When it reacts with a base, it can also form salt and water. So it's right there in front of you. The amphoteric oxide acting like a base when it is reacting with an acid, or it acting like an acid when it reacts with a base. In both the cases, it is capable of forming a salt and water, which is much similar to a neutralization reaction. So what I'm going to do is that I'm going to at least write two examples which have been really common in past papers. One of them is zinc oxide, and the other one is going to be aluminum oxide, which I'm going to write below. So take your time while you're noting it down. So 6HCl, 2AlCl3 plus 3H2O. So it's doing almost the same thing. All right.
I see.
So whether it's the example of zinc oxide or the example of aluminum oxide, in both the cases, they are acting in one equation with an acid and one equation with an alkali and neutralizing to form salt and water. The same salts are actually given on the next page, page number 127, and the names sodium zincate or sodium aluminate have been mentioned. So whether it comes as a word equation or as a symbol equation, I think now you're capable of writing both. Since word equation was already a part of the book, symbolical equation would be something extra and it would be good for you because these equations have been a part of past papers. Whether you talk about past 5 years or 10 years, yeah, they have been a good part of it.
Right,
When I say
sir.
good, I am talking about repetitive questions, questions which have been repeated. And I've seen that out of the 6 examples for amphoteric oxides I've quoted above, uh, these two are the ones that I've seen most used, zinc oxide and aluminum oxide. And even the book contains just these 2 examples as oxide over here. Now, we are left with last one. Can I clear this whole thing up? Hmm? Can I clear this whole thing up? Are you done writing?
Yes, sir. Please, sir.
All right. So we are left with the last example, neutral oxides. Now, neutral oxides consist of water, carbon monoxide, nitrogen oxide, and let me tell you, apart from water, carbon monoxide and nitrogen oxide are insoluble in water. Okay, since they're insoluble in water, they're not going to dissolve, they're not going to go with any litmus test, and more most probably they are not going to give any kind of neutralization equation. So oxides which act as an acid are known as acidic oxides. Oxides acting as bases known as basic oxides. Oxides acting as both are known as amphoteric oxides. Oxides acting as neither are known as neutral oxides. So it's pretty simple to understand and bifurcate these 4 types of oxides. And I hope you find them easy too, right?
Yes, sir.
Good. This finishes 5.3 for us. Now remember, 5.3 is a big topic. It has examples, it has definitions, it has equations, and on top of everything, there are a lot of colors involved. Flame colors, colors for litmus, whether they're going to turn red, blue, or the appearance of products as gases or solids along with their colors. So there is a lot to memorize as in terms of facts in this topic. So make sure you do because these memorization points have been tested in Cambridge way too many times, which actually finishes the topic. Let's come to 5.4. And this is a small topic, so we can find it out really quickly. So acid reactions in everyday life. Now, I'm not going to go with these whole topics. There are a lot of paragraphs, a lot of words. You don't exactly need to memorize everything. So we're going to simply underline a few things and try to remember them. So the hydrochloric acid is the acid which is present in our stomach, which helps us to digest our food. Sometimes the stomach produces excess acid. This causes indigestion. To ease this, we take antacids. Antacids or antiacids are a group of compounds that have no toxic effects on the body and they simply neutralize the effect of acid indigestion. Milk of magnesia is a great example of that. It contains magnesium hydroxide, which is alkaline in nature. Okay, moving on. I'm gonna skip this one. You know the fizziness in most of the tablets or soft drinks is due to the carbon dioxide they produce. So let's just simply skip it, move on. Okay, descaling cattle. Cattle sometimes have a buildup of white salt at its bottom. This is known as lime scale, magnesium or calcium scaling. That happens with continuous consumption of kettle for boiling water. Now, this usually happens in the hard water areas. What can we do to treat this? You can't just simply scrape it off or scratch it. Vinegar can be used to descale kettle. Without damaging the metal, they can react with the carbonates and actually decompose them or consume them. Commercial descalers use other solutions such as methanoic acid. Remember, the formula to methanoic acid was HCOOH. So from here to here is the only part that you need to understand and memorize. Okay, moving on, I'm going to clear it up. You have a table over here, table 5.6. This talks about different vegetables and the pH of soil, the range of pH in which we should grow them to have maximum yield. Now take a look at them. You will find that the pH range is very weakly acidic from some of these, a little bit around um, neutral for some of these, and sometimes a little bit over the neutral range for some of these. I guess it's pretty easy for you to understand that different soil pHs are actually beneficial for different vegetables. Let me tell you, you do not need to memorize this table. Okay,
Okay, sir.
moving on to soil pH and plant growth. Now, soil can have different pH. That's true. Rains, acid rains, the use or consumption of fertilizers, the soil can be acidic or alkaline. In this entire heading, I suggest my students to cover this paragraph, the last paragraph, page number 128. And this paragraph is really simple and straightforward. If your soil is too acidic, you can treat it by liming. Liming or lime, the formula for which is CaO, is a loose term which either means calcium oxide. You may also mean calcium hydroxide by it, which means CaOH twice, or powdered chalk or limestone, which is calcium carbonate, which means CaCO3. These compounds will neutralize the acidity of soil. Now, if the soil is too alkaline, on the other hand, we cannot use any acidic substances. Like we were literally using some alkaline substances when the soil was acidic, but when the soil is alkaline, we cannot use acidic substances. What do? We dig in some peat, the soft form of coal, or decaying organic matter such as compost, manure, animal waste, fallen leaves, anything like that. But why do we do that? We do that because all of these are organic material. Organic material is eaten up by bacteria. Bacteria then in turn produces the acid which neutralizes the alkali.
Sir, could you explain this again?
Yeah, I'm saying this organic material would be eaten up by bacteria or microorganisms, simply speaking. Now, bacteria in turn will produce acid as a waste, and this acid will neutralize the alkaline soil, right? So it's a stepwise process. So farmers are um, clever enough not to directly put acid into the soil. There's no point in doing that. Most of the acids are reactive. They're going to react with different materials in the soil. Instead, throwing in some peat, which is the soft form of coal, decaying organic matter, compost, manure, fallen leaves, fallen part of plants, unused part of plants that we don't require or you need to use. And in a matter of few days, bacteria are automatically going to eat them up, produce acid as a base, and that acid is going to neutralize the alkaline soil. Get the point?
Yes, sir.
Good. Let's move on. If you're done writing, can I clear the whole thing up?
Yes, sir.
All right. Moving on. Great. Hydrangea, flower that can produce different colors based upon the acidity of soil. If the soil is slightly acidic, pink flowers. If the soil is neutral, purple flowers. If the soil is slightly alkaline, blue flowers. And you can see different colors right in a small picture, which means if soil is acidic at one step and you take one more step and right over there on to the next step, the soil is slightly alkaline, you'll have uh, one kind of flowers on in one hand of yours and other kind of flowers in the other hand of yours. This is how attractive it is, and that's how human came to learn about indicators and acidity of soil as well. So we say many flowering plants have their own built-in pH indicators. Let me tell you, some indicators do come from plant sources. Next up is effluent in wastewater treatment. Effluent is the waste that can flow out of the industry. So liquid waste from factories is often acidic. If such waste gets into a river, the acid will kill the fish and the other river life. This includes the plants as well as the fish. Slate lime, which is commonly known as calcium hydroxide, that is CaOH twice, right? Slate lime is often added to waste to neutralize it. Slate lime is similarly used to treat streams or rivers or lakes affected by acid rain. But what we can do, something even better, is that we can reduce the emissions of sulfur dioxide. Now, we have studied this specific topic in chapter 1. Many modern factories and power stations now spray acidic waste with bits of flake lime in flue gas desulfurizer. We also call it scrubber. Remember, scrubber was a big pipe which had showers of water or sometimes showers of flake lime so that when the gases pass through them, right, instead of them being converted into acids or neutralized, they would get neutralized right there in the factory, inside the industry, and the industry is only going to throw out neutral waste, not acidic waste. So that way we can lower down the number of acid rains on the planet. And that is a really good idea. It's just showers of water or showers of flake lime, and they can easily treat that acidic gases. Since sulfur dioxide was part of acidic oxide in the previous topic, I hope you remember that. Okay, so
Yes, sir.
this does not just end up over here. This topic has a separate portion, the portion which was a part of this specific topic 5.4 in the previous version of the book, but in this version, if you go way back in the very starting page of chapter 5, you find that portion. There it is, nature's defenses, things galore. Now, methanoic acid, as we were discussing earlier, the formula for which is HCOOH, has the name methanoic because of formic acid. The word formica literally means ant, and whenever it stings you, it injects you with methanoic acid under your skin. That's why you have such a scratchy feeling. You would really want to scratch that part of the skin because of the acid stinging inside of your body. Now you can utilize this sting by rubbing some baking soda on it. Baking soda or sodium hydrogen carbonate, the formula for which is NaHCO3, as we have previously discussed in the big table on the third or fourth page of this chapter, that is a part of our kitchen, is alkaline in nature, and can easily neutralize uh, the acids that are present in this thing. These things also contain methanoic acid, right? They also contain other highly acidic chemicals. In contrast, the wax thing, which is different, its thing is alkaline. Now you can neutralize that alkaline deal with lemon juice, maybe with tomato juice, maybe with apple juices, which contain citric acid. So I have already discussed this topic with you under the name of spillage. And this time we're talking about the different things. All right, Claire?
Yes.
So these are very simpler, easier examples. And with studying this part, we actually finish up both 5.3 and 5.4 for today's work. And I think that's good enough for today. We are going to start with 5.5 in the next sitting, which is about alkalis and bases and differentiating between them. Since we have been using both the words, it's about the high time that you understand the difference between both. We are hopefully going to do that in the next sitting. Any questions?